Yeah, so in this lesson, we want to continue from where we left off yesterday. So solving diagonalizable system and then introducing the notion of inner products in vector spaces. And then if time still allows, we'll just toss in the discussion of projections, you see. So without wasting time, so let's get to it. So now we have an idea of what diagonalizable systems are. What we want now is to learn how to actually solve them. How to solve diagonalizable systems. Something is wrong. Yeah, so that's what we want to look at the moment, how to solve a diagonalizable system. So first we want to define what systems are we talking about, because the system that we're going to be discussing in this section are not the ones that we have seen in the earlier chapters, the linear systems. So these are still linear systems, but they're linear system of differential equations. You see, so the systems that we will solve are systems of the form x prime is equal to some matrix block times A, like that, where here we just have some matrix Aij. So these are simply written as system like this, where the matrix is represented by A, like that. So what we want is to learn how to solve systems of this nature, so which we call linear system of differential equation or first order differential equations. So these systems, they can be classified under two classes as diagonalizable and non-diagonalizable, depending on the matrix that is involved. So if A is diagonalizable, we call it a diagonalizable system. If A is non-diagonalizable, then it becomes a non-diagonalizable system, like that. But what we want now is to focus only on one category, which is that of diagonalizable system. So how do we solve diagonalizable system? So suppose the n by n matrix A has the eigenvalues lambda 1, lambda 2, up to lambda n, which correspond to the eigenvectors v1, v2, v3, up to vn. Then the solution of, so let's call this equation 1, like that, you see. So then the solution of 1 is given by x is equals to alpha 1 v1 e to lambda 1 t plus alpha 2 v2 e to lambda 2t plus plus alpha n vn e to lambda n t, like that, you see. So this kind of like summarizes the whole process of how one goes about solving what we refer to as a linear system. So what we have here is an expression which shows us exactly, or a statement which shows us exactly what we need in order to solve a linear system which appears in the form 1. So if you are given a system like the one which appears in the form 1 and you're asked to solve it in exams, so the first thing that you need in order to solve such a system is to find the eigenvalues and the corresponding eigenvectors for the matrix A associated with the given equation. So finding eigenvectors and eigenvalues is something now that we have seen how it works. So how do we then construct a solution out of that? So this here shows us how exactly this should be arranged in order for us to obtain a solution of any given linear system. So you see that you always have some exponential terms which are functions of t, and t is a coefficient which is the eigenvalue of is a typical eigenvalue of some matrix A. And in the coefficient, we have a product of a scalar quantity, lambda 1, and V1 is the corresponding vector for that respective eigenvalue that you have there, like that. You see. So all this written in an abstract way is just something which summarizes the whole process of how one goes about solving linear system. So solving linear system is just doing all this work. So to demonstrate it, we're going to look at one example, which I believe it will be enough to demonstrate. So an example that you can get in exam is whereby you are asked to solve. So we are given this problem, and then we are asked to solve this system. So how do we go about solving? So we know that in order to construct a solution for this type of system, we need to obtain the eigenvalues together with their corresponding eigenvectors. So what we're going to do is we are going to then take this matrix and define it to be A. So we let A be the matrix involved in the problem. So we extract it and call it A like this. So what we're going to do now is we are going to find the eigenvalues of A. So for eigenvalues of A are given by, so the eigenvalues that we're trying to look for of A, they are given by 2 minus lambda minus 2, 4, then 0, 3 minus lambda minus 2, then 0, minus 1, 2 minus lambda equal to 0, like that. So what we're going to do now, we know that this determinant equation is what we need to solve to get the values of lambda. So from here, we know how to proceed that this expands as follows. It becomes 2 minus lambda times 3 minus lambda, negative 2, negative 1, 2 minus lambda, then minus 2 or plus 2, lambda 0, 0, negative 2, 2 minus lambda, then plus what we call this 4. Then with 4, we have 0, 0, 3 minus lambda, negative 1, all that equal to 0. So we see that these first two terms will go to 0, and this one will go to 0 because when you take your products, you will get 0. So it follows that here we have 2 minus lambda, and then this and that, they will give us what? 3 minus lambda, 2 minus lambda, so minus 2 equal to 0. So let's simplify. So we get 2 minus lambda, Then if we expand these two brackets, we get lambda squared. So minus 3 minus 5 lambda. Then we have 6, then minus 2, so plus 4, all equal to 0. So let's see if this factorizes. So we have 2 minus lambda here. So put lambda both sides. Then look for factors of 4, which gives us 5. So I think it's -1, -4. So it factorizes nicely for us. So therefore, we can conclude from here that lambda is equals to 1, 2, 4. So these are our eigenvalues for this given system. So now we have to find, for these eigenvalues, the corresponding eigenvectors. So how do we go about that? You see. So for eigenvectors, V, we know that, you see, so if we have some eigenvector V, we know that A, V must equal some lambda V. So let's try to find what these V are. So to find them, we'll let V be given generally some coordinates alpha 1, alpha 2, alpha 3, like that. So this implies now if I were to multiply the matrix given, which is 2 minus 2, 4, 0, 3, minus 2, then 0, -1, 2, times alpha 1, alpha 2, alpha 3. This must provide us with alpha 1, alpha 2, alpha 3, like that. So let's then try to figure out one equation that we can use in this. So there's something nice which comes, especially if we consider the second row. So from row 2 now, what do we see? Do you see that if you have to take row 2 and multiply, you will get that 3 alpha 2 minus 2 alpha 3 is equals to lambda alpha 2. So we have a very nice thing that simplifies nicely there. And then again, we can take the first row. So from first row, we have that 2 alpha 1 minus 2 alpha 2 plus 4 alpha 3 is equals to lambda alpha 1. So we have these two connections, which I will just call connection 2 and connection 3, like that. So we have to now solve these equations for different cases of lambda. So now, when lambda is equals to 1, what happens? So when lambda is equals to 1, what happens to our equations? So we see that from the first equation, if you plug in 1 here, you will have alpha 2. So this will come here and we have 2 alpha 2. So it will come to us that alpha 2 is actually equal to alpha 3, like that. Then again, what will happen is if we put alpha 1 here again, we'll get something of similar sort, because this will become alpha 1, it will come here, subtract, we'll be left with alpha 1 minus 2 alpha 2 plus 4 alpha 3 equals to 0. So this implies, since we know that these two are the same, we can eliminate one of them. So I can either replace alpha 3 with alpha 2. So I'll get that alpha 1. If I use alpha 2 here, so I'll have 4 alpha 2 minus 2. So I'll get plus 2 alpha 2 equals to 0. So this implies alpha 1 is equals to -2 alpha 2. So now we've managed to write everything in terms of alpha 2. So it implies in this case, V becomes, so we'll call it V1 because it corresponds to lambda 1. It will be alpha 1, which we have found to be negative 2 alpha 2. Then also we have alpha 2, and then alpha 3, which is also alpha 2. Factor alpha 2 outside, we get negative 2, 1, 1. So we see this is our eigenspace, and we can take that as the eigenvalue. You see. Then now we shift on to a new case where lambda 2 is equals to 2. So what happens when lambda 2 is 2? So when lambda 2 is 2, we'll have 2 here. So when we have 2 here at this lambda, this 2 will come and we'll have alpha 2. These 3 and 2 will cancel, will subtract, and we're left with 1. So we'll remain with alpha 2. And then we can throw this term that side. So we have alpha 2 is equal to 2 alpha 3. Like that. Then again, we are placing 2 here. So if we place 2 here in terms of alpha, these 2 terms will cancel. So alpha 1 will vanish. You see, so alpha 1 will just vanish. Remember, when a term vanishes like this, it becomes a free term. And whatever result that we'll get here is similar to the one that we already have. So we'll still have alpha 2 is equal to 2 alpha 3, and alpha 1 is free. So what does that mean then? So this implies that V2 that we're looking for is actually equal to alpha 1, alpha 2, which is 2 alpha 3, and alpha 3, which is just alpha 3. Then we can split these to become alpha 1, 1, 0, 0, plus alpha 3, 0, 2, 1, like that. You see, so you can take any one of these as the eigenvalue that you want. Because remember, you can choose this arbitrary, so you can choose this to be 0 and take that to be 1 so that you choose this or whatever that you like. So we have that. Then let's go to alpha lambda is equals to 4 now. So when lambda 3 is equals to 4, what happens now? So we go there to our solve problem. So here now the value is 4. So when this is 4, I can take 3 this side to come this side so that I have 4 minus 3, which will give me just lambda 2. So I'll have lambda 2 is equals to negative 2 alpha 3. So I have alpha 2 is equal to negative 2 alpha 3, and same thing, put 4 here. I'll have 4 alpha 1, take this alpha 1, I'll get 2 alpha 2 is equals to all that. And I'll have 2 as common thing, so I can divide so that I'm left with alpha 1 is equals to 2 alpha 3 minus alpha 2. So I'll be left with alpha 1 is equals to 2 alpha 3 minus alpha 2. So what I have to do now is, I know what alpha 2 is. So this implies alpha 1 can now be written as 2 alpha 3 minus 2 alpha 3, which will give us 4 alpha 3, like this. So we've managed to write everything in terms of alpha 3. So what does that mean? So it follows that V3 is going to be alpha 1, which is 4 alpha 3, and alpha 2, which is negative 2 alpha 3, and alpha 3, which is just alpha 3. Factor out alpha 3, what remains is 4, negative 2, 1. So that's our eigenvector. So now we know our eigenvalues and their corresponding eigenvectors. Now it's time to write down what the solution of our system is. So using the result that we have seen before, we can therefore write that the solution is what? Solution is x, which is usually a function of t, is equals to c1 times v1. So what is v1? So v1 we can take any, so we take negative 2, 1, 1. So we put negative 2, 1, 1 here. Then it's going to be e to alpha 1, where alpha 1 is just that. Then plus c2. C2 again, you choose your, for lambda 2, you choose, so you can take 1, 0, 0. So you take your 1, 0, 0 here. Then you will have e to alpha 2t plus c3 e to 4t. So for the last one, which is here, you can take this as your eigenvector. So you'll have 4, negative 2, 1. So this then becomes your solution for your linear system. So any questions on this?
No. I went through the work in the morning, and I think it's much more clearer how you explained it to me, because I was a bit confused in the morning, but now it's much clearer.
Okay. So if it's not much clearer, then that's good. So this is how we solve these type of systems. So you just have to practice them again now and see if you can now get them right without facing any challenges. So just redo a lot more different problems. Let's see. Otherwise, yeah, that's it about linear system for non-diagonalizable system. This is taught in the 2DE course. So, but if it happens that it's asked here, you can use the skills that you've learned in 2DE to do the same thing, because you're not restricted in any way in using what you learned in other fields to apply in other fields. Easy.
Okay, so I'll do that.
So now we are moving on to another new concept in linear algebra, which is the concept of inner products spaces. You see, so now we want to discuss inner product spaces. So what is the whole idea of inner product spaces? You see, so the whole idea of inner product spaces is actually to generalize the dot product. You see, because remember the core of the whole of linear algebra is all about vector spaces. You see that? And when we talk about vector spaces, we usually picture the objects that are contained in a specific vector space to be vectors, you see. And though they are not actually the same vectors that were used when it comes to physics, but our goal in linear algebra is to actually treat them the same way we do with the vectors that we know of, you see. So if you have done some bit of MEM 1000, you have been introduced already to three-dimensional vectors where you were given situations like -2, 4, 3, and another vector, b equals to 7, -6, 5, and then asked to find things like a dot b. You see, I think you've come across something like this.
Yes, I have.
Easy. So
yes.
So this is what we call the dot product. It is something that exists within the domain of these objects that we call vectors. You see. So what abstract algebra is seeking is that it tries now to bring in this idea of vectors also to work in the realm of vector spaces, like that. You see, so this whole section, the whole point about it is to just generalize this idea. So to generalize this idea now, we have to now use terminology or yeah, let's just refer to the terminology that can then work with all these different types of vector spaces that we have seen, because we have seen in our study that matrices actually they form a vector spaces, functions can form vector spaces, and many other different objects can form vector spaces. So now if we want to generalize this idea, then we have to try and use suitable notation which can cater for all these different types of objects, you see. So now we start the generalization of this idea by defining exactly what a vector space or an inner product is, you see. Because here in vectors, you are just taught how it's done, but we do not go far to the abstraction of what is happening here and then putting all that in a more abstract way. But now this chapter is going to do something like that, whereby we actually observe deeply what's happening and then write some sort of an abstract theory out of what we've seen. You see. So what is an inner product? You see. So given a vector space V, an inner product is the map from V to R such that which is defined as follows. You see, so what we actually call an inner product, it is just a function. It is a map which takes out from the vector spaces into the real numbers, you see. So a number or a map which is defined in such a way that it takes two vectors and it maps them into a space of real numbers is what we refer to as an inner product of vector spaces. So it is something which is actually seen here, because if you take a closer look at what is happening inside there, you will start with vectors, meaning you start with an object, it's a vector. At the end of the day, you end up with a real number. So which means actually what we are doing every time when we're computing the dot product, we are performing a map from one domain to another domain, where the other domain is that of vectors and the other one is of real numbers, like that, you see. So it is just the observation of this point and then now abstracting it. So now in an abstract way, that's what we mean when we define an inner product. So an inner product is just a map which takes us from V to R. The function itself, remember for function, we always use the symbol F and whatever, but for an inner product, we just use the bracket notation to represent it. So here and here are spaces that are left for two elements of a vector space to enter, so that when they enter here, they are computed to produce a real number out of it, you see. But how is it defined? So how is it defined? So, and this object is an object which is such that it takes two elements of a vector space, maybe let's call them V1 and V2, and then produces some real number out of it, you see, like that. So for now, that's all that we have, you see, about an inner product. So that's what we have. So this thing that we call an inner product, it has the following properties. So the inner product is the following properties that you must be aware of. that it doesn't care how in the order in which you put things inside the bracket notation. So even if you start with V and end with U, it is the same thing that you'll get when you start with U and end up with V, like that. So this property of the inner product, we refer to it as the symmetry property, like that, you see. Then two, there is another nice result which says that if this element V is split into two parts, which becomes V1 plus V2, and we keep the other one intact as U, then this thing can distribute this way with the left element. So we have V1 U plus V2 U. I am confusing now, using different techniques to represent that. So this is another property that it has, you see. So this is what we call a linear property. So it satisfies what we call the linear property, but actually this is bilinear. The same thing can be done also with the element on the right, because this will follow from the above that you can switch things. So since you can switch, it means you can switch the order of things, still the same rule will apply, like that. So this is one of the things that has to be known. Then also there is this property that if one of the elements is being multiplied by a scalar, if you have this times U, then you can pull out the scalar so that you just have the inner product between the vectors defined like that. You see. Then the last property that the inner product has is that if you have V dotted with V, then this will always be greater than 0 all the time. You see. So equality if this thing is equal to 0, then the vector V must be the 0 vector itself, like that. So this is the information that we have to know when it comes to inner products, that they satisfy such results. So these are properties of which comes together with this object that we call the inner product, you see. But now we've seen that, okay, the inner product is a map which takes us from V to R, and it has these properties. But how do we actually perform an inner product between two elements coming from a vector space? How do we construct a real number out of that? You see, so to construct a real number out of two elements of a vector space is something that is distinct depending on the vector space that you are aware of. If the vector space that you're dealing with is that of the normal vectors, these ones, then we know how to perform an inner product. But how does you perform an inner product when you move to a new vector space, that of matrices, that of functions, and all that stuff? You should know how actually you can perform a dot product in those type of sets. So now let's talk about them. Let's talk about all these different things.
Sorry, could I ask a quick question about number 4?
Mm-hmm.
So you say there's the V vectors, right? There's two V vectors.
Mm-hmm.
So is there, like, the first one would be 0, or is it just it has to be equal to each other, whatever the V is?
Yes, it has to be equal to each other, whatever the V is.
Okay. All right. Okay. Thank you.
Okay. You see, so now we want to talk about inner product with functions. So the inner product with functions. So how does one perform an inner product with functions? Since functions can be looked at as if they are vectors under different operations, how then can one define something as an inner product with functions? You see, so there is one usual way that we use most of the time when we want to define an inner product with functions. And what is that usual way? You see, so if we have two functions, f and g, which are element of C, A, B, like this. So what it means is that f and g will be continuous function in the interval AB. That's what this means. So suppose you have two functions which are continuous, or you have a vector space of functions that are continuous on the interval AB, how can you define an inner product? So if you have two functions A and B, one can define an inner product as follows. So the inner product between function can be defined as fg is equals to integral from A to B of f times g dx, like that, if both these two functions are just functions of x. So one common way of defining an inner product in function is by making use of an integral and a definite one, because why it has to be definite, we want to have some real number at the end of the day. So we want to start with two vectors extracted from a vector space, and we want to come up with the real number at the end. So this is one way of defining what we call an inner product with functions, like that, you see. So what about other different vector spaces? So what is the usual way? So inner product with matrices. Inner product with matrices. So what is the common way of defining an inner product within the space of matrices? You see, so if V is a vector space of matrices, and AB are elements of V, then an inner product in V can be defined as follows. You see, like that. So when it comes to matrices, one way of defining an inner product in that space is by using the trace of the product, you see, because you know that the trace actually is going to be a real number. So in order for us to get a real number out of that, then this is how we can suitably define it. You can construct many other ways. You can also use the determinant, because we know also that the determinant is one way of associating a number with matrices. But it's just that one of the reasons why it may be
sorry. So the network is breaking up.
Okay.
The last thing I heard was trace.
Okay, sorry. Okay, so I was just saying that there are many ways of associating a number to a matrix. One is by using the trace, the other is by using the determinant. So what I'm trying to say is that there are many ways of defining an inner product within a vector space. You see, it's just that one of the reasons why you're more likely to fail with the determinants is because whatever definition you provide, these properties must always hold true. You see. So you will see that when you use the trace, it's easy to have most of these properties holding true. But if you try to use the determinant, some of these properties will fail to hold true, no matter how you define the inner product between those two matrices like that. But again, this works mostly if the product between A and B is something that can be evaluated. Otherwise, if it's undefined, we cannot do it that way. So we have to define it in such a way that we know that it's going to hold true for all elements in V, and it's the properties of that we expect to hold also must hold true, you see. But what we have just shown here is one of the many ways that one can use to describe an inner product between other vector spaces other than the space of normal vectors, you see, like that. Then the norm. You see. So now let's talk about the norm. So if now we have a vector space in which an inner product has been defined.
So,
hello?
So I think it's my signal it keeps on breaking up. Let me put mobile data on quickly rather than Wi-Fi.
Okay. You see, so as I was saying that the norm, and immediately when we define an inner product in a given space, there are some other things that actually can be defined within that vector space. So one such thing is the norm, you see. So if V is a vector space in which an inner product has been defined. So if V is a vector space in which an inner product has been defined, we define the norm of some element V in big V as which is equal to like that, you see. So if you have a vector space and there's an inner product already that has been defined within that vector space. So for each element in V, we can define another object which is called the norm of that element. So the norm of that element is just the root of this quantity like that. And we know that this is going to hold true because we've shown already that this quantity is always non-negative. So the root of this quantity is another quantity which we define the norm, and the symbol for that norm is like this. You see, so it's the absolute sign and the object placed inside. So we call that the norm of a vector like that, and it's defined in that manner. So it is one of the things that you should be able to perform or to find for each object contained within a vector space, as long as they exist an inner product that has been well defined within that space. You see, like that. So that's what we refer to as the norm. So this norm has the following properties, you see. And the following results hold true for the norm. So for this quantity that we call the norm, there are some certain results that actually hold true for it that can be proved. So the result one. So it's called the Schwarz inequality. So the Schwarz inequality, it states that if V and U are elements in V, then the, what we call this, the norm of U, of VU, is less than or equal to the norm of V times the norm of U, like that. So there is this result, which we call the Schwarz inequality, which is defined as follows. It says that for any two objects that come from a vector space in which an inner product has been defined, that inequality will always hold true, like that. Then also there's another one, which is the second result, which is the triangle inequality. So the triangle inequality is another one, an inequality again, which holds true for the norm. So it says that if V and U are elements of some vector space V, then the norm of the sum of U plus V is less than or equal to the norm of the individual sum of V plus U, like that, you see. So these are quite important results that you have to know, which go hand in hand with what we have defined here, the norm of a vector space. So they are not quite used, but it's very important to know them. Just to know them, it may be quite important most of the time that these results, they hold true whenever we are discussing this quantity that we have defined called the norm. You see, so I think you're familiar with all that. Then
yes, the triangle inequality comes up quite a bit in DE.
Yes, that's it. Even if you did real analysis, it's more often there. Okay. You see. So yeah, this is most of the stuff that we need. But then the last item that you want to also introduce in these type of vector spaces in which an inner product exists is the angle between two vectors. You see, so the angle between two vectors. So the fact that with vectors, we know that they exist, the concept of the angle within that domain. Since we are trying to generalize the dot product of that domain to also be applied in all the other areas, it means we try to make sure that the notions that exist within that field, we also bring them to exist also in this other field, you see. So now with other vector spaces, which are not even vectors themselves, which can never be represented using arrow diagrams, one of the interesting things about linear algebra is that they exist a notion of an angle in all vector spaces. But it's just that now this angle is something that you cannot visualize, because now when you talk about angle, most people, they talk about the measure of a turn between two straight lines. But in linear algebra, the angle is just a notion which has similar properties to the angle that you are aware of, but it's a different thing as we move from one space to another space. Do you get that?
Yes, I do.
You see, so you have to be careful when it comes to that we calculate something called an angle, but in your mind, you must not visualize it as the actual angle that you have been measuring using a protractor. What? Because what will you measure now when we talk about matrices? Because this thing can be generalized to apply in matrices or in other different vector spaces. So it's hard to then visualize what an angle is. So there's just a notion, but no visual property of it. But how exactly do we find this angle between two functions? You see. So if V is a vector space in which an inner product has been defined and V1 and U are elements of V, then we define the angle alpha UV between the vectors V and U as follows. You see, so the angle is defined as follows. So alpha UV is equal to a cosine of the inner product between U and V divided by the norms of U times the norm of V, like that. So if for within anything that is called a vector space, where there is a way of defining an inner product, there is the notion of the angle that we can also associate with that space, which is defined as shown there, you see. So in the whole study of inner product spaces, this is something that you must be familiar with and know how to evaluate, you see. So now let's do one example just to practice what we have learned. But before we go on to solving problems, are there any parts where you would want us to re-explain the theory that we've discussed so far?
No, it's fine for now. I think after a few problems, it would be much better.
Okay. So what kind of problems should you so example. Suppose V is a vector space of functions F elements of C01, you see. And suppose that we define an inner product in V as below. You see. So suppose the inner product in V is defined as below. It is FG equal to integral from 0 to 1 of FG dx. You see, like that. So here we consider a situation where we have a vector space of functions which are continuous in the interval from 0 to 1. So in this vector space, we have defined an inner product in that manner. You see. So now, suppose f of x is equals to 2x squared minus 1, and g of x is equals to 5x plus 2, like that. And then evaluate the following. So this is one typical problem that you can get in exams. So they will say evaluate the following: f, g, then b, the norm of f, then c, the angle between f and g, like that. So these are typical problems that you can get in exam. They can give you a vector space and then tell you how an inner product in that vector space has been defined. Then they can give you some explicit objects in which they want to see if you are able to actually perform certain operations. So the first question is saying find the inner product between the two functions f and g. So now how do we find that? You see, so to answer the first question, part A, we want to find the inner product between f and g, and we know that is defined as integral from 0 to 1 of f times g dx. So it means I have to find the integral of 0 to 1 of f of x, which is 2x squared minus 1 times 5x plus 2, then dx, like that. You see. So what we have to do now is to use what we know about integration to simplify this. So we get 0, 1. Then we expand here, we get 10x cubed. Then we get plus 2x squared. Then we have minus 5x minus 2 dx. So what do we get now when we integrate that? So increase power by 1, divide by the new power. So if we increase there, we get 4, divide by that. We have 10 over 4, which will simplify to 5 over 2, x to 4. Then here we have 3.
Sorry, sir.
Hello?
Sir, shouldn't it be 4x squared?
4x squared. Oh, okay, 4x squared, sorry. 4x squared. I see what you mean. It's 4x squared here. So even this now becomes wrong. So thanks for that. So we have 4x squared. So we increase the power, so we get 4 over 3 that. Then we have negative 5 over 2x squared. Then we have negative 2x. Then all these evaluated from 0 to 1. So we see that with 0, everything is going to vanish. So what do we get? Put 1, we get 5 over 2 plus 4 over 3 minus 5 over 2 minus 2. These cancels, and what do we get with the other terms? Minus 2/3. You see. So which means the inner product between f and g is just simple, minus 2/3. So we see we started with 2 vectors, we end up with a real number, which proves the that what we call an inner product is actually a map from vector spaces to the real numbers. You see. Then the second question is asking for the norm of f. You see. So we want the norm of f. So we have to recall, how do we define the norm of f? We know it is the square root of the inner product of f with itself. You see. So that's what we call the norm. So it means now first I have to evaluate what is underneath the root side. So now, what is ff? So according to the definition that we have given, f f is going to be the integral from 0 to 1 of 2x squared minus 1 squared dx, if not mistaken. You see, because it's f times f, which gives us that. Then let's simplify. So it's 0, 1. So that squared, we have 4x4, then minus 4x squared plus 1, then all that way. So now let's integrate. So here raise, so we get 4/5 x5. Then you have negative 4/3 x3, then plus x, all the way from 0 to 1. So 0 vanishes everything. So we have just 4/5 minus 4/3 plus 1. And what is that? Equal 2. So if you have a calculator, you can work it out faster, because I don't see any short way of doing it. So in my calculator,
it's 7/15.
So we see this is what we expect. So that's the norm. You see, so we get that. Then C. So with C now, we want the angle between the two vectors. So we want the angle between f and g defined as follows. And we know according to definition that this angle is given by arc cosine of the norm of f and g at the top, the inner product of f and g, then divided by the norm of f times the norm of g. So which means to calculate this angle, the top two, we already know what these are. So we have to get g, the norm of g now. So what is the norm of g? Sorry, I forgot to put here the answer here. Remember what we just calculated is this. So we have to root it to get the norm. So we have to say root of that. Easy. So yeah.
Okay. In our answer, can we just put root of 7/15? We don't have to rewrite the root and so everything inside.
Yeah. So now we have, let's find GG. So GG is going to be 0, 1 of 5x plus 2 all square dx. So what will that give us? 0, 1, then 25x squared, then 10, 20x plus 4 of dx. So what do we get here? So we increase here, so we get 25/3 x cubed, then we get 10x, then plus 4x, so it's 10x squared plus 4x, then all from 0 to 1. 0 vanishes everything, so we have 25/3 plus 14, and what do we get? So what do we get?
60/3.
Yes, 67/3, like that. So now how can we evaluate the angle now? So therefore the angle that we're looking for is going to be alpha fg equal to arc cosine of what? So we put at the top, what did you get for the f dot g? So f at g, it was -2/3. So we put -2/3 there at the top. Then at the bottom, we have the norm. So the norm of f, we found that it was root 7/15, and the norm of g is also root 67/3. So we just have to simplify that, and what do we get? So you can punch it and also your side, so that we know for sure that, yeah, what we are doing is the right thing.
I got minus 0.2065.
It's minus It's minus what?
Mine is 0.2 065.
So it's in radians, I guess.
Yes, yes.
And for me, it's 102 degrees. So that's it about a evaluation of inner products. We are doing with the same thing that we're doing with vectors, the normal ones, but now the definitions have changed. So the only thing that changes as we move from one vector space to the other vector space is that the way we evaluate the inner product is quite different, but all the notions are there completely. So everything that you do with normal vectors can be done with all other objects in mathematics, you see. So that's one nice thing about this subject of abstract algebra, because it gives us, it tries to unify different objects to behave as if they're just one thing. So yeah, for today, I think, yeah, time is no longer on our side. We can just stop here.